Thank you. So I'll continue today. Yesterday we discussed 1D lattice models, realizing various fusion category symmetries and studied their Hamiltonians, which realize all possible gapped phases protected by these symmetries. Today I'll describe the 2D counterpart to this story. So just to get on the same page, let me first quickly review gauging conventional Z2 symmetry on the lattice. So consider a hexagonal lattice. With qubit degrees of freedom on each plaquette. So I have a two-dimensional vector space at each plaquette, and there's some Pauli X and Pauli Z operators acting on this vector space. And there's a Z2 symmetry. Let me denote the Z2 symmetry as S. And this is just the product of all sites, sigma X. And for simplicity, let's consider most conventional Hamiltonian, which is just minus of Zi, Zj, just the transverse field Ising model. And so yeah, the vector space, this model is just tensor product of all sites, qubits at a site. Now, if you want to gauge this, the gauging procedure follows in a couple of steps. The first step is to just extend the Hilbert space. So extend the state space. And the extended state space now has also degrees of freedom on the edges. So here. And I'm going to denote the Pauli operators acting on the sites as X and Z, and those acting on the edges as X tilde and Z tilde. And now in order to gauge the symmetry, we need to impose some Gauss constraints. So there's a projector, P Gauss, which is just the product of projectors on each site for 1 plus Gi over 2. And Gi is just the operator that has the local representative of the Z2 symmetry, as well as X tilde does. So if I define a basis, for instance, on this vector space, let's say the basis is labeled by phi I and aij. This is, I'm diagonalizing the sigma z and z tilde operators. So zi is just minus 1 to the phi I aij, and z tilde is just minus 1 to the aij. Then one can see that this Gauss operator generates gauge transformations, as we're familiar. So I can define some G lambda, which is product of I Gi to the lambda I, where lambda is 0 or 1. And this thing just sends a state phi I aij, phi I plus lambda I aij plus d lambda. So it's just the usual gauge transformation implemented on the lattice. And so we want to go to a singlet under this gauge transformation. So yeah, first we extend the Hilbert space, we impose some Gauss constraint, and we also minimally couple the Hamiltonian such that it commutes with the Gauss operator. And minimal coupling, the minimal coupled Hamiltonian is just minus VI. Sorry, I'm describing this. I'm sure all of you are already familiar with this, but it'll help to generalize to kind of non-minimal gaugings, which I'll describe subsequently. So just bear with me, just to make sure we're all on the same page. So this is the minimally coupled Hamiltonian. And now we want to, so, but the Hilbert space is constrained. So the gauged Hilbert space is this Gauss projection operator acting on the extended Hilbert space. So we want to solve this Gauss constraint. And one way to do that is there's a unitary operator, which I'm not going to write down. It's an easy exercise to work out what it is. But the way it acts on operators is it sends xi, zi, x tilde I, z tilde, sorry, ij. Okay, sorry. So let me define this operator as x, I, b, I, b. So this is the usual plaquette operator of toric force. I'm just calling it b. There's such a unitary, it's some product of control x's or something, and it implements this operator map. And one can see that, let me call this H gauged. This is H. So UH gauged U inverse is just minus Z tilde ij minus lambda summation I BPI. And the Gauss operator is just xi. Now we can solve the Gauss constraint readily because we just need to, we just freeze the degrees of freedom on the plaquettes. And then we have a Hamiltonian that's written purely in terms of the degrees of freedom on the edges. So we started off with a model that has a Z2 symmetry. A natural question is, what is the symmetry of the gauged Hamiltonian? So, sorry, I should also say that there's an additional constraint here. So if you look at a vertex on this lattice, then the operators Zi, Zj, Zj, Zk, Zk, Zi, which was 1 before gauging, after gauging maps to Z tilde ij, Z tilde jk, Z tilde ki, which also must be 1. So this is actually a constrained Hilbert space after gauging. I mean, after solving the Gauss constraint, it's still constrained. So we have this constraint, and this is the Hamiltonian. And so one can see that this has a symmetry. The symmetry is generated by lines, by operators defined on some line gamma, where gamma is non-contractible line on the dual lattice. And just the product of Z tilde ij's. Ij belongs to gamma. And this is a one-form symmetry generator. I'm sorry? So yeah, if your Hilbert space, if your lattice is on a sphere, on a two-sphere, there's no non-trivial action of one-form symmetry. It acts trivially on all states. But if you have a torus or something else, then it can act non-trivially. So this is a Z2 one-form symmetry. And it's interesting to ask what are the how operators map between these two theories. So if I take some patch and define the S operator on a patch, this is Z2 zero form symmetric operators, and these are Z2 one form. These are the operators in the gauge theory. And this thing maps to a charged line. So this
BP operator
yes.
is made out of X tilde.
Sorry?
This BP
yeah.
is made out of X tilde operator.
Yes, this is BP. X tilde is on the boundary of a plaquette. So if I take some open patch and define the symmetry operator on that, then after gauging, it becomes a product of X tildes on the boundary of that patch. This is a version of the statement that you might be familiar with, which is twisted or disorder operators go to charged or order parameters or symmetry breaking order parameters. This line, this product of X tildes on the lattice is charged under this one form symmetry. Meanwhile, if I take a single sigma Z somewhere at some site, upon gauging, it becomes a semi-infinite string of Z tildes on the dual lattice. And the precise location of this line doesn't matter because this line is topological, and moreover, you can move it using this constraint. So this is a statement that charged operator goes to twisted operator. This is a very general statement in quantum field theory or lattice systems or anything. Yeah. Yes. Yeah. Yeah. Usually you want to only talk about symmetric operators, so you take some other Z at infinity, or if you have, or you can think of this as a twisted sector operator with symmetry line going in time direction if you're in some quantum field theory. But yeah, I think it's easiest to define it on the infinite lattice. So this is kind of very, yeah. This one? So this operator, so if I take Zi, Zj times Zj, Zk times Zk, Zi, that is the identity operator, right? And this map is an algebra preserving map, if you wish. It's a bond algebra isomorphism. So there's some algebra of operators here, Zi, Zj, and X form some algebra. And the same algebra is formed by these operators, Z tilde and BP. And so if there's some operator which is the identity, it should map to the identity. So this is, therefore you get a constraint. Yeah. 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 So in 1D, you don't get any, yeah, you'll get the same degrees of freedom. Yes. For each contractible cycle, the product of Z tildes on that cycle on the dual lattice is the identity. And this is also the statement that the one form symmetry is topological. If you didn't have this, you would have some kind of non-topological. You can impose this energetically if you wish, if you just want to study this model. And then you might discover this one form symmetry in the low energy subspace. But if you want to have this one form symmetry in the entire parameter space of the model, which is what you should have if you gauge in an honest way, then this is the constraint. You have yes. Yeah. So you want to add some kind of field strength. So if I add like a Z The magnetic field here would be Z tilde. Yes. Yes. So I'm imposing a flux-free constraint on the gauge theory. No, I mean, if I start with this model and I just gauge, I need to impose that this operator, which is the identity, and I see what it maps to after gauging, right? So this is some operator on the extended Hilbert space. At this level, this is an operator. Yeah. So on the gauged Hilbert space, that's an operator. And then I just do a unitary transformation. And that operator maps to the product of Z tildes on a closed loop. So look at this operator. You agree this is the identity, right? And now I just that's right. You're right. Yes. Oh, sorry. I need to minimally couple also. I need to minimally couple each of these, and then I get a closed loop of Z tildes. So I have to add Z tilde ij here on each of these. And then I get a closed loop of Z tildes, which is 1. I see. Yes. So you're saying I could have added a Z tilde here? On any closed loop. And this is gauge invariant, obviously. I see. Yeah, maybe we can discuss this after the talk. Yeah, but I agree with you. I agree with you, yes. So yeah, but in any case, there's this map of operators, mapping twisted sector to charged operators and charged operators to twisted sector operators. Yes. 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 Yeah. So I want to localize this G. This U operator, I can tell you later. It's some product of control X's. We can discuss that also. I mean, it's easy to write down. Okay. So, but this is kind of a general story. If you start with some G symmetry, one can gauge subgroups or the full group and realize various dual symmetry categories. So for instance, if you gauge all of G, then the dual symmetry is something which is rep G one form symmetry, which is also called 2 rep G. If you gauge some normal subgroup H and G, then we find some 2 group symmetry in general. And for a non-normal symmetry, we'll find some non-invertible symmetry category. Non-condensation, non-invertible symmetry. So I want to say something about the kinds of symmetries one might find in 2D, and there's like a generalized gauging procedure one can carry out to realize a very large family of symmetry categories. If you look at fusion 2 categories, there was some math result from, I think, November of 2024, which classifies this into two families. One are called all boson fusion categories. And the other so-called emergent fermion. And the distinction between these is, so you can take any fusion category and look at its genuine lines. And in general, those genuine lines might braid with other lines in the symmetry category. However, there's some subcategory of transparent lines, those that braid trivially with everything else. So for these, the transparent lines form rep-G. And for the emergent fermion type fusion categories, the transparent lines form rep of a supergroup. So I'm going to be focusing on this kind of fusion categories today. And the nice thing is that what one can do is start from any category of this type and just gauge rep-G. So one could have gone back from the one-form symmetric model and gone back to the zero-form symmetric model. So you can gauge rep-G. It's non-anomalous. And doing so, one finds some category which is essentially like a group. So there's some G prime, let's say, possibly with anomaly, stacked with the two category corresponding to some modular tensor category. And these are kind of easy to construct on lattice. So what one can do is do the converse thing, start from a model which is G-symmetric, stack on it some MTC, and then gauge some diagonal. So this has some symmetry G, and you can gauge some diagonal and go back. So this is just, so M is some modular tensor category, so it has some lines, and you can add all possible surfaces that are constructible using those lines. And that's what I'm calling sigma M. It's the condensation completion of M into a two category. Yeah. Sorry? Yeah, I think for the purposes of this talk, it's not very important. There's some surfaces. There's some surface topological defects that act on all of space. There are some lines, and there are some consistent fusion rules between them. There's a long list of consistency conditions that they need to satisfy. But I don't think I would need to get into a lot of technicalities of two categories. Or maybe I can introduce them as we go along. So what I want to do is describe some generalized gauging procedure. So the procedure I want to describe is essentially something like the following. You start with a G-symmetric model. and you stack on it some topological order. So I'm only going to be talking about non-chiral topological orders. So it's the Drinfeld center of some fusion category. Let me call it A1, and it has an H symmetry. H is a subgroup of G. It's possibly non-norm, and you gauge H. And then find some dual lattice model. This procedure is effectively the arrow going back from this group-like category stacked with an MTC to any general all boson type fusion category. So again, we start with some a model on a hexagonal lattice with G qubits on the sites. So V is and then we go to an extended Hilbert space, which is a tensor product of C. Okay, sorry, maybe I should step back a second. So the structure of a modular tensor category that has an H symmetry can be captured in some fusion category A, which is H graded. So in this whole construction, this fusion category would play an important role. Physically, you can think of it as follows. So I'll just postpone this for a second. So you have some theory which is Z of A1. A1 being the identity grade in this H-graded fusion category. Now this has a Dirichlet boundary condition, and the lines on the Dirichlet boundary condition form A1. This is just the canonical, the construction of, so you can construct the Drinfeld center from A1, for instance. Furthermore, there are some defects here which implement this H symmetry. So for each object, each group element H in capital H, there's a symmetry defect. And if one brings this to the boundary, you get some lines that live in the H grade of this fusion category. And you can take fusion of these surfaces, and that gives you the correct graded fusion of these objects on the boundary. And there's a way to recover this H symmetric, this HSET, from the data of this H graded fusion category. Any questions about this? So I want to go to an extended Hilbert space and impose a Gauss constraint, just like we did here, and recover some gauged model. So on the edges, I add a Hilbert space that is basically the rank of, as the dimensionality, the rank of this fusion category, so the number of objects. And further, at each site of this lattice, we impose a fusion constraint. So this is a constrained Hilbert space. If I have A, we impose that AIK is in the fusion product of It's kind of like the Levin-Venn state space. There's this fusion constraint here, project onto the subspace that satisfies the consistent fusion rules. And now we can define a Gauss operator. So yeah, now to go to the gauged Hilbert space, this is some projection from the extended Hilbert space. And what this P Gauss is a product of, same as before, some GIs, where GI takes some configuration let me make sure I get that one. This kind of plaquette constraint, Levin-Venn plaquette constraint, except for each group element H, you sum over all line operate, or you change the element from GI to HGI, and this state can be evaluated by fusing the line X onto the boundary using some F moves, for instance. Yeah, so you'll see, so far there's no difference, but when we solve the constraint, we'll find different state space depending on whether, so at the end you can solve this, and the degrees of freedom on the plaquettes are labeled by cosets, by right cosets of H, and structure of those depends on whether it's normal or not. So as I was saying, this diagram can be evaluated by you partially fuse it and then evaluate these by some F symbols and then contract the bubbles. By the way, the special case where A is just vec H, this just corresponds to twisted gauging. So you paste with a new SPT and then gauge H. So this is ordinary twisted gauging. Now we can partially gauge fix like we did earlier. And gauge fix, we noticed that some configuration made a mistake. So we can see that we can partially solve this Gauss constraint using this property. And what it gives us is that the plaquette degrees of freedom are labeled by right cosets, right H cosets in G. We get this gauge Hilbert space V. Which is this is the set of right cosets. States in the state space are labeled by HI, which are representatives of right cosets, and objects on the edges, and these objects then also satisfy this fusion constraint. And there's one remaining constraint which is not solved, which is this Levin-Wen plaquette constraint, which is further imposed on this state space, which is there's this Levin-Wen plaquette operator. With objects in the identity grade of this fusion, of this G-graded, H-graded fusion category. Where LIX is just yeah. Yeah. So I start with, so what I'm trying to do is start with the G-symmetric model and effectively stack and gauge. The initial degrees of freedom are just this. So you just have G qubits on the plaquettes. And then I add extra degrees of freedom. The extra degrees of freedom are added on the edges. So I've also assumed that maybe I didn't say it, I've assumed that the fusion category is multiplicity free. So I don't need to add anything on the fusion spaces. So the only thing I add is degrees of freedom on the edges. And I add a state space whose dimension is the rank of A. Then I impose, and there's a fusion constraint, which projects onto the state space where the fusion is satisfied, the fusion in A. So I'm describing the gauging procedure. Yes, so that corresponds to this. That corresponds to this case. So for each group element H, little h and capital H, you have a single object. That's so you get an H dimensional degree of freedom on the edges. That's just the usual gauge field. I'm saying instead of having a single degree of a single vector for each group element on your states, on your edge state space, you have as many vectors as objects in that grade. So like, yeah. Because I want to do a more general thing, and the more general thing involves stacking with some MTC and then gauging, a non-chiral MTC and then gauging. If I didn't want to do that, you're right. I would just be introducing some H And you see the rank of A is just the order of H, if A is vec H. Yes. Yeah, so recall the Z2 case that we did earlier. In that case, A was vec Z2. So I was just introducing 2 degrees of freedom. The number of objects in vec Z2 is 2. I was introducing 2 degrees of freedom on each edge. And I was viewing vec Z2 as a Z2 graded fusion category, which you always can. And then imposing this Gauss constraint. So if you translate this back to vec Z2, you recover the old Gauss operator. No, this is not twisted gauging. I'm saying that a special case of twisted gauging is untwisted gauging. Earlier we did untwisted Z2 gauging, but we could have also added an extra twist. The extra twist just appears when you fuse these bubbles. So, yeah. So to fuse these bubbles, you need to first move it past this junction, and for that you need some data of nu. The nu is the F symbol in this category. So twisted gauging is a word that's used for stacking an SPT and then gauging. And the SPT is labeled by nu. So if the SPT is non-trivial, then this is what you have to do. Any more questions? Yeah. Yes. Yes. So yeah, then there are no dynamics here because it's TQFT. Yeah, but the spectrum should be the same. Let's say on a sphere, the spectrum would be the same. Yes. This would also preserve the local physics because those, I mean, locally, well, yeah, so there is some entanglement, for example, that you would add. You'd be able to locally diagnose things. But I'm just, on the lattice, I'm trying to implement stacking and gauging. It's not the conventional gauging. Yes. Yes. Yeah. Yeah. Yes. Yeah. Maybe the degeneracy is on because of the open string operators, you mean? Yeah. Yes. Yeah. It remains the same in, I mean, for example, if you, the symmetry broken phase maps to a symmetric phase. In the symmetry broken phase, you have 2 ground states. So in a sense, the symmetric subspace maps to a single state. That's so for ordinary gauging, degeneracies can change, but yeah, because charge sectors get mapped to twisted sectors. So if you look at all possible boundary conditions, then you can map. So the spectrum of some charge sector with some boundary condition maps to some other charge sector with another boundary condition. So let me give an example this, which produces an interesting phase. like yesterday, let me start with S3 symmetric model. So we have 6-dimensional state space at each plaquette, and the symmetry of action is just UG. Now I can consider a Hamiltonian. Let me start with a Hamiltonian for the S3 symmetric model that breaks the symmetry down to Z2. So it's a Z3 SSB phase. A Hamiltonian looks like the sum of terms on plaquettes and terms on edges. I should say I'm using the same presentation for S3 as I did last time. So S3 is generated by A and B, and So I want to construct a Z3 SSB phase. Let me describe the Hamiltonian. It has two kinds of terms. One are local on-site terms, and then there are terms that involve two plaquettes. HI. Acts with the right on this, and HIJ acts on an edge. And imposes a delta function kind of constraint. One can see that the ground state of this Hamiltonian, there are three ground states where you have like a disordered sum over group elements on each plaquette that belong to the same left coset. So the left set of left cosets is, let's say, M0 is 1B, M1 is AB. Exactly. In this case, H is 1 and B. It's a Z2 subgroup of S3 that has the elements 1 and B. B is an order 2 element. This H, so this just imposes that GI, GJ inverse is either 1 or it's B. So there are three ground states. Exactly. The left cosets. You get these three ground states, and the symmetry acts on these as follows. So you have GS0 GS2 and GS1, 0, 1, and 2. And the asymmetry maps between these. Meanwhile, the B symmetry, the operator, acts invariantly on this while it swaps these two. This is just the natural action of S3 on a triangle. And what I want to do is I want to gauge Z2 first without stacking anything, and then I'll describe the gauging with stacking. So already we'll find an interesting phase. So let me say something about the symmetry. Maybe I'll describe the gauging first. So now if we gauge Z2B, what we find is a dual model where the gauged Hilbert space has degrees of freedom on the plaquettes that are labeled by right cosets, sorry, by left cosets. And then there are Z2 degrees of freedom on the edges. And there's also a flatness condition on this. You can see the gauge. So I should say that the left cosets. So these were the right cosets. What we find is a Hamiltonian, the gauged Hamiltonian. So this operator just acts with the B. It's a right action of B. The group A, Z2B, and one can see that. So this is again okay. So the right action with B swaps these two cosets. So it acts. Meanwhile, it acts invariantly on this. So what HI tilde becomes is in this case 1 plus gamma I BI P over 2, where gamma is okay. So sorry, maybe I'm doing this in the wrong order. So let me step back again. Sorry. So there's a three-dimensional state space on each plaquette, and there's a two-dimensional state space on each edge. Let me write down this. Let me define a basis on edge gauged, labeled by A, P, where P is 0, 1, 2, and Q 0, 1, right? And I'll define some, and I've taken representatives of each coset. So the representative of this is 1. the representative of this is A, the representative of this is A squared. And I'm labeling my states with those representatives. Now I define some operators on the sites. Zi acting on AP is just omega to the P AP, where omega is and then there is a charge conjugation operator which sends AP to A minus P. So these are the operators that I'm going to describe the Hamiltonian using. And this gamma I is basically the same one here. And BP is the same product of sigma x's on the boundary of the plaquette that I described earlier. Now what Pij does is it's a projector. So earlier it was a projector onto the 1B. So the edges need to be the edges need to be in the group H. And what Pij does in the gauged model need more space. Some gauged Hamiltonian. What H tilde Ij does is it projects onto a subspace. So if you have Gi or A to the Pi Hij, when we say Gi Hij Gj, then we want Gi Hij Gj to be there's some projector that projects onto configurations of this type. So if these two elements are the same, if this is 1, then these two elements have to be the same. If this is B, then these two elements have to be inverse of each other in C3. And that's because the action of B on M1 prime, which was the left coset, maps it to M2 prime, while it leaves M0 prime invariant. So now, the nice thing is that this Hamiltonian can be now solved quite easily, and the low energy state space actually splits into two. So splits into some space V0 for which P is 0. So it's in the image of this projector, but P is 0. And in this state space, the Hamiltonian on V0 is just 1 plus BP over 2. Plus the flatness constraint, which is sigma z over 2. And this is nothing but the toric code Hamiltonian. So one of the ground states in V0 is just the toric code. Meanwhile, the other ground state in V1, for which P is not equal to 0, HV1 is 1 plus BP sigma tilde x. And this sigma tilde x is an effective degree of freedom that acts on the 1-2 space. This acts on P equal to 1, 2 subspace. Plus the plaquette, plus the flatness constraint. And this is just a trivial phase. Z2 enriched trivial phase. So we get two vacua, two ground states that look very different. One is a toric code ground state, and the other is a trivial paramagnet. And there's some symmetry that maps between these two. This would, I should say, this would never be the case if we only had an invertible symmetry, right? There would never be two ground states, one of which would be topologically ordered and the other topologically trivial. Yes. Yes. Mm-hmm. Yes. Yeah. So these, I gauge the Z2 symmetry. Yeah. Which has two ground state and one of which is topologically ordered. It's a okay. So the Hamiltonian, this is what the Hamiltonian looks like. The sum of two terms which commute, right? And this term is a projector onto configurations that look like this. Yeah, exactly. So P0, 1, 2, it denotes the left cosets, and they're the degrees of freedom on the plaquettes. Meanwhile, yeah, and there's some qubit degrees of freedom on the edges. Yes. Now, this projector, Hij, projects onto configurations that look like this. Now you can ask what the Hamiltonian does. It acts, so first we project onto this subspace, and it turns out under action of this operator, this subspace splits into two subspaces. One of them is V0, for which P is 0, and the other is V1, for which P is not 0, it's 1 or 2. Right? So on the P equal to 0 subspace, we can look at the Hamiltonian. On the V equal to 0 subspace, this gamma acts trivially. Because gamma sends P to minus P. It's like a charge conjugation, if you wish, is on the Z3 degree of freedom. So since this subspace is invariant under the action of gamma, the Hamiltonian just becomes the toric code Hamiltonian on the nose. Right? So this is the ground state. The ground states of this Hamiltonian are this is a toric code realized in this subspace. Right? Now, if you look at V1, the Hamiltonian in V1 is the trivial, realize the trivial phase. Yes. Yeah. Then you'd get, so if you start from S3 trivial phase, so single ground state, and you gauge S3, then you'd get the rep S3 SSB, which is a rep S3, which is like the S3 Dicraft-Witten theory. And the symmetry is generated by the Wilson lines of that theory. Yeah, so you'll get a S3 quantum double, and that quantum double has some line operators labeled by rep S3, which are the charged lines, and those will generate a rep S3 symmetry, which would be spontaneously broken. because you also have flux lines that braid with it. No, it'll be topologically ordered. Yeah. So you'll have, yeah, rep S3 SSB. Yeah. So actually it's very simple if you look at this figure, because from the perspective of Z2 that we are gauging, this is like a paramagnet. While this is these two form like a ferromagnet. So this multiplet of states splits into paramagnet plus ferromagnet. And if you gauge it, the paramagnet goes to toric chord while the ferromagnet goes to the trivial phase. And that's exactly what's happened. So it's, if you just look at this, it's not surprising. Yeah, exactly. You had a question also? So of course, this could be generalized to, yeah. So following up on your question, Sergej, this could also be generalized to some other group. Say you start with, I mean, a mild generalization would be if you start with some dihedral group and you have a Zn SSB, let's say n is equal to 6. Then you have some 6 ground states. 1, 2. And Z2 acts like this. While Z6 just goes around the clock like that. Now, if you gauge Z2, you just end up with a toric chord coming from 0 and then trivial coming from 2, 6 and so on. Trivial from 3, 5 and toric chord from 4. So it's just that actually, this is all that has happened, but in some like slightly more detailed, like, yeah. 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 Yes. Yeah. Yeah. So the recipe is that you look at the initial phase and it has some symmetries and some order parameters. Those are the deconfined defects in the yeah, those are just order parameters, let's say. Now, when you gauge, you just see what those map to. So if the symmetry is broken, you have a charged order, local order parameter, if it's a conventional symmetry, and it maps to a twisted sector operator. If it's a twisted sector operator, means the symmetry is trivial because the symmetry defect can end. So the symmetry is not broken. Instead, if you have a twisted, if you start with the symmetry preserved, some symmetry is preserved, let's say H is preserved, that means you have twisted sector defects of H. And when you gauge that, those become charged lines at the end of these surfaces, and they organize into some conjugacy classes. And that means that the dual symmetry is broken. So if you just track the operators that exist in the ground state manifold of the original theory, then you can figure out what are the operators that act within the ground states of the gauge theory. Those are the order parameters. That tells you the phase. So I don't have a lot of time, so maybe I just summarize what the generalized gauging would give you in this case. So imagine you did this, except instead of gauging Z2, you gauge Z2 in this generalized sense, right? So let's say you start from here, from this thing. Is that a question? And you gauge non-minimally, so you gauge using some algebra A, which is A1 plus AB. In this case, what one would find is, instead of toric chord, you'll find the state that corresponds to the Drinfeld center or the Levin-Wen ground state of with A as the input fusion category. Meanwhile, so this would be the analogous thing to toric code. Meanwhile, the analogous thing to the trivial state would be Z of A1. And just like this is the Z2 gauging, the toric code is the Z2 gauging of the trivial phase. The ZA is the Z2 gauging of ZA1. So over here we gauged the subgroup Z2, right? So more generally, instead of gauge, so the degrees of freedom that we added were 1 degree of freedom for each group element. Now, when you gauge, you can do more generally gauge with a fusion category graded by Z2. So instead of adding a single element for each group element, you add a grade of a fusion category. And then you go through this whole procedure, you impose these Gauss constraints and so on. Eventually, the Hamiltonians that you'd find would have just the same number of states on a sphere, but the role played by toric code would be replaced by the Drinfeld center. So if A is easing, you'd find easing quantum double, and you find 2 toric codes. And easing is related to toric code by some Z2 gauge. It's also intriguing to look at a further generalization of what you were asking, Sergej. Imagine instead of a finite group here, if you had a continuous group, so you have some G, which is, and there's some outer automorphism action of Z2. Say this is U1, and this is actually O2, the whole group. So it's interesting to ask, if you have a GSSB, you have some manifold of states, which forms, say, a circle in this case, or some group manifold, and then you gauge some subgroup, in this case Z2. You get some orbifold space, and there might be some fixed points, like 0 and pi in this case. Those fixed points seem to look different from the points that are mapped into each other from the perspective of this gauging. So there should be some distinction between these points and the rest of this manifold of ground states. And I think this has not been studied too much, as far as I know. Yeah, there's some paper, but it's interesting because like gapless phase, but also mixes with topological order in some sense, because some states in this Goldstone manifold look different from others after you gauge them. Twisted sector lines can end on like here you can so more specifically, if you look at this ground state space and you ask, can I couple this to a Z2 background gauge field? You shouldn't be able to do it at any general point in this manifold because Z2 is broken. But you can only do it at some specific points, or you can act invariantly with an open Z2 symmetric operator. So you'll take your Z2 symmetry operator on an open patch, and generically, if you act with it on some vacua, you'll go out of the ground state space. You'll get some excited state. But there are some special points where if you act with it, you get back the same state. But now when you gauge the symmetry, the bulk of that Z2 operator disappears, but the boundary becomes a charge line under the dual symmetry. So it looks a little bit like toric code. This is a kind of peculiar feature because you also have like gapless modes, but you have something that looks a bit like topological order. So far, I only described gauging, but one can also look at non-minimal or generalized Hamiltonian. So I could fix a state space and ask, can I deform the Hamiltonian to go to different non-minimal phases? And we saw yesterday that one could do that. So there was this anion chain, and you could write down Hamiltonians that were labeled by algebra objects in the input category C. And they used some co-multiplication and multiplication in this algebra. So, and then the other thing was to change the module category and gauge the symmetry. But so far, I've only described changing the module category. What about Hamiltonians? So it turns out that the models that I was describing so far can be formulated as something called fusion surface model. Which was introduced in this paper by Kanse and Kantaro. And I should say most of what I discussed today is in this paper. So in this fusion surface model, it looks a lot like the anion chain, except you have some two category in the game. So just like we had a row here, you have some object in this two category, which are surfaces. They consider something slightly more general, but for now, this would suffice. So this kind of a configuration gives you a state. From lambda I. And also something on the vertices. And there are some constraints. This is still a constrained state space. So you could take some endomorphism of lambda I, and that will give you the same state in this Hilbert space. Now the Hamiltonians. So one can construct Hamiltonians, so non-chiral Hamiltonian, non-chiral gap phases. Are again classified by just like Hamiltonians here were classified by Frobenius algebras. Here they are classified by algebras in this two category. And these algebras, I should say, these are classified by H-graded fusion category. Where H is some subgroup. So very unsurprisingly, the same data describes the gauging as well as the gap phases. So given some H-graded fusion category A, one can construct a Hamiltonian that basically looks something like this. It's the analog of this structure, and it acts on this kind of a state from above. And so the objects in this, let me label the objects in 2vec G as B2G for all group elements in G. So in general, this algebra A has a direct sum of H in H. You take the H, the object corresponding to the group element H, and take as many copies of it as the rank of that grade in this fusion category. And then you impose some fusion, you impose one morphisms. So for example, these have to, so I can take some D2H1 times fused with D2H2. And there are as many choices as the rank of H1 and H2. So I can label them by some other indices, alpha and beta. And this goes to D2, H1, H2, gamma. And these one morphisms are completely specified by this algebra A. So you can look at this and read and kind of construct this algebra, this structure of surfaces. And also there are two morphisms. So just like realizing SPTs, SPT Hamiltonians in 1 plus 1D, there was some additional data over here. There was some data over here that was some multiplication M, which was dictated by a 2 cocycle and some co-multiplication. Here there's a 2 morphism here, which is labeled by a H3 class. So this 2 morphism is this is specified by the F symbols of this fusion category. Now, given all this data, one can read off how to act with such an operator on a state space like this, and that produces all non-chiral gapped phases with G symmetry. Yeah, so in 1 plus 1D, let's say you start with G symmetric model and you want to realize an SPT. What that means is you have to choose an algebra, which is H comma beta, and then the symmetry will break down to a subgroup H and it'll realize an SPT beta, all that. But the way you actually construct the Hamiltonian is you use beta to construct these morphisms. So there's a morphism from A to A tensor A, and from A tensor A to A. And the precise data of this morphism is just read off from beta. So concretely what it means is whenever you see H1, H2 going to H1, H2, you act with the phase H1, beta of H1, H2. And you engineer a Hamiltonian that produces this phase whenever you see this kind of a fusion. Now, the analogous thing to that is instead of these one morphisms, you have two morphisms. And these two morphisms are given by the associator in this fusion category A. So you just use this associator to see how such a structure would act on a state, and then engineer the Hamiltonian that does that. So I'm out of time, but let me just say one last thing to wrap up, that this whole construction can be contextualized in the SIM-TFT. So we have a SIM-TFT. And for any fusion category C, which is Morita equivalent to 2-vec G, stacked with this empty C, this SIM-TFT is just a die-Kraft-Whittle, 4D die-Kraft-Whittle theory for the group G. Now, there are some standard boundary conditions, which are Dirichlet and Dirichlet. Taking these two boundary conditions and compactifying this produces the SSB phase. Now, over here, basically what I described is that you can gauge you can gauge these lattice models using the data of a H-graded fusion category. And in general, if you take that fusion category, it corresponds to a new boundary condition, which is Dirichlet stacked with Z of A1 and gauging H. Meanwhile, if one can write down lattice Hamiltonians, which are also graded by another fusion category. Let me call it B, and let me say B, which is K graded. And this is A, this is H graded. So there are two boundary conditions that one can produce using the same data. B graded, so you get again Dirichlet stacked with the Drinfeld center of B1 and gauging K. So now when we compactify the SIM-TFT, we produce the gapped phase, which would correspond to generalized gauging with A and choosing a Hamiltonian labeled by B. So that's the map between the SIM-TFT construction of gapped phases and the lattice construction.
Okay, questions? There are no immediate questions to raise around